Okay, and number one, write a function that can replace g of x so that the system of equations shown in the graph becomes an infinite solution system. So the first thing I need to do is identify what each of these equations are. So we have our function f of x, which is equal to, let's see, it has a y-intercept at -6, and it has a slope where we go up 1, 2, right 1. So it has a rise and a run, rise of 2, run of 1. So our slope is 2/1, which is just going to be 2. And our y-intercept is over here at -6. So my function will be 2x minus 6, because we're writing it in the form mx plus b. My function g of x has a y-intercept of -2, and then it has a slope where we go up 1. So rise of 1, run of 1, 2, 3. So for this one, the y-intercept is -2. My slope, I rose 1 and I did a run of 3. So the slope is 1/3. So g of x is equal to 1/3 x minus 2. So slope of 1/3, y-intercept of -2. Now the question specifically is saying, write a function that can replace g of x. So honestly, don't really care about g of x anymore. So that it becomes an infinite solution system. So I want something parallel to that function. Now technically, we could just change the slope so that it's something that has a different y-intercept, but same slope. So we want a different y-intercept, but the same exact slope. That way, when I look at it on the graph, it will be parallel to this g of x value. So see how it has the same slope, but maybe it has a y-intercept of -6. Okay, so I'm going to maybe call my new function h of x. Just so we know it has a different name. And so for it to be parallel, it has to have the same exact slope. So our slope has to stay at 2. So it'll be 2x. And then in order for it to have a different y-intercept, I can technically pick whatever I want because we are talking about like I'm writing whatever I want. So the only thing that I can't let be would be -6. Because again, I want a different y-intercept. And if I picked -6, that's the exact same. If I picked -6, then my solution would be infinitely many. Oh my gosh, I didn't read the question correctly. I'm so sorry. I saw it right at the last minute. Okay, so it says infinitely many. I am really sorry about that. I'm going to just write on top of it because I know some of you may have already written that. So we definitely still want the same slope, but the opposite of the different y-intercept. We want the same. So if we had the same y-intercept and slope, that means that we are going to have infinitely many solutions. If you have a different y-intercept and the same slope, just so we can clarify this, that would be your no solution. Okay, so there are two polar extremes of this question. So you either want infinitely many solutions or no solutions. I really apologize for misreading the question. It wants an infinitely many solutions. So we want it on the exact same line. So we actually do want my b to be equal to -6. So be -6. Now, granted, we could change the function slightly, like it could be rearranged. Maybe I had factored it out. So this is kind of your what if scenarios. So if this were a multiple choice question, it may not be so obvious because if you look at our answer of 2x minus 6, it's the exact same. So it's probably not going to be that obvious on the quiz. But maybe I would write it as 2 times x minus 3. That's the same thing as up here if I just distributed in the 2. So just be familiar that maybe your options wouldn't be so obvious as the exact same. I'm really sorry about that conclusion, but it came up with a good discussion. If the question wants no solution, you want different y-intercept, same slope, and you can pick whatever. If you want something for infinitely many solutions, we want the same y-intercept and same slope. So that was this note over here. Okay, number 2, consider the following system. What can you change the second equation? So we're changing the second equation so that the system will have no solution. I'm gonna circle it this time so I don't mess that up again. Answers will vary. So this is set up for elimination. Now thinking, if we want no solution after elimination, we want something where it's like 7 equals 0, something that's impossible. Now, for the sake of the last problem, I had kind of done both scenarios. If I had something where it was like 0 equals 0, that's where it's always true. And that would be our infinitely many solutions, which we'll actually go into on the next problem. Okay, but question on hand. So we want to change the second equation. So we're stuck with this x plus 2y equals 4. So my goal is to multiply this by something so that all my variables cancel and I'm left with something like 7 equals 0. So something that's not possible. So looking at this x plus 2y equals 4, well, looking at the equation below it, we already have a negative x below it. So that is a good sign. So we definitely wanted to maintain having like a negative x. However, if I were to add these together, 2y plus y, that would become 3y. So I would need to change it so that it is maybe a negative 2y. So let's make a note. I changed that plus y into a negative 2y. So now when I add these together, I purposely didn't finish that for a reason. When I add these equations together, x plus a negative x becomes 0, so that term cancels. 2y plus a negative 2y, those variables also cancel. So we're still just left with 0 on the other side. So this is the pivotal moment where, looking at my problem, I want it to have no solution. So I want to make sure that whatever I end up putting right here, when added to 4, it does not give me 0. So we can honestly leave it. Leave it as a 2. So we have 0 equals 6, and now we get no solution. Okay. Now, if the question had wanted always or infinitely many solutions, I would actually have wanted to change that positive 2 into a negative 4 so that it would have canceled out. So the question of like, how would I change it? I would change it to the equation negative x minus 2y equals 2. Because I wanted it to be something that when added to the previous equation or the top equation, the variables all cancel and it leaves me with a not true statement. That's the opposite for number 3. Number 3, consider the following system. What can you change the second equation, negative x minus 2y equals negative 10, so that the system will have infinitely many solutions? So I'm looking to multiply this by something so that I get 0 equals 0. Now at the moment, if I add these together, 3x plus a negative x, that would be a 2x. Now, if I want to eliminate this, I need, let's see, my top equation is staying the same, so let's just leave that as a note. 3x plus 4y equals 40. I'm going to backtrack slightly and just make sure that I circle this. So this is, we're looking for infinitely many solutions, just so I don't forget it again. Okay, so I need all my variables to cancel. So I need this negative x to become a negative 3x. So that when added to the equation above it, the x's will cancel. Okay, I have a positive 4y. In order for that to cancel, I need a negative 4y. So I need to change this to a negative 4y. And then finally, we currently have a negative 10. If I wanted a no solution, I should leave it. However, I want infinitely many, so I'm going to change that to be a negative 40. So that when I add those together, the x's would cancel, the y's would cancel, so we're left with 0. And 40 plus a negative 40 also cancels, and we're left with 0 equals 0. And that's what we want for infinitely many. So to answer the question of write or change the equation, I'm going to change it so that it says negative 3x minus 4y equals negative 40. Now looking back at number 2, just so we're clear again, thinking about this graphically, no solution is any parallel line to the given line. There's so many different options of how you could have gone about it. I try to just take like the most direct way of like, how could we change this so that we get no solution? So that's what I came up with that. However, for the infinitely many, we really only have one option because it has to be the exact same line. Now, granted, I could have technically like multiplied it by something, because if you do scalar multiplication by a linear function, it doesn't actually change the function, but we're just going to keep it simple. Okay, numbers 4, 5, and 6 are getting down to kind of more direct, just solving, because we're getting into the quadratic systems. So to solve this system, we want to use substitution. So I'm going to set each equation equal to each other. So we have a negative 5x plus 9 is equal to x squared minus 5x minus 7. I see that there's an x squared in the problem, so I want to set it equal to 0. So I need to add 5x to both sides and then subtract 9. So we now have 0 equals x squared. Coincidentally, those 5x's also cancel, minus 16. So you can either solve this by factoring or solve it by square rooting. It doesn't technically matter. So I'm going to add 16 to both sides. So we have 16 equals x squared. And then I want to square root both sides. Whenever I square root both sides, I include plus or minus. So I get x equals plus or minus 4. To find, so these are points on a graph. So we would have a 4 point and a point at negative 4. To find the y coordinates that correlate to those x values, we are going to plug this back in, and it doesn't matter where we plug it back in. I try to find the simpler one, which in my opinion would be the linear function. So I'm going to plug in a positive 4. So we'll have y equals negative 5 times positive 4 plus 9. So that would be a negative 20 plus 9, which is a negative 11. Second, we plug in the negative 4. So we have negative 5 times negative 4 plus 9 equals, let's see, that would be a positive 20 plus 9 would be 29. And these would be our 2 final answers. Okay, for number 5. Same deal, we have 2 functions, both set equal to y. So to solve the system, we're going to set each of those equations equal to each other. So we have 2x plus 5 equals negative 3x squared plus x minus 4. I see the x squared. I actually prefer to keep my x squared positive. So I'm actually going to move everything over to the left. So I'll add 3x squared. I'll subtract x. And I will add 4. So we will have 3x squared. 2x minus x is x. 5 plus 4 is 9 equals 0. So my first instinct is to try to factor this. Don't write this down. Again, don't write this down. I'm just going to talk about it. If I try to factor this, I would try to put the 3 in the cloud, and I would have x squared plus x and then plus 27. I don't have two numbers that add to equal 1 and multiply to be 27. So factoring is not a possibility here. I still want to try it to see if it would work because that's simpler. But unfortunately, in a case like this, it's not going to work, which is why I did not want you to write it. So that forces us into using the quadratic formula. So our quadratic formula, if you did not know it, is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And in our problem, a is equal to 3, b is equal to 1, and c is equal to 9. So our problem will have x is equal to the opposite of b, so that's a -1, plus or minus the square root of b squared, so 1 squared is 1, minus 4 times a, that would be a -12, and then -12 times 9. Just make sure. -12 times 9 would be a -108. So we have a -108 all over 2a. So 2a would be 2 times 3, which is 6. Okay, when I do 1 minus 108, I get a -107 all over 6. Now, a negative under the radical means that this is going to be imaginary. We're not looking to find imaginary solutions, so we would just stop right there and say there are no real solutions. And that would be our final answer. So a little, I think kind of like a red flag goes off when you see that it can't be factored. So that's why I jumped right into the quadratic formula, kind of hoping that we would get that imaginary solution. And it's validated when we see that there's a negative under the radical. Okay, number 6, starting off the same way. We want to set our two equations equal to each other. So I'll have x minus 1 equals x squared plus x minus 1. I see the x squared, so we need to set this equal to 0. I like to keep my x squared positive, so I'm going to subtract x and add 1 to both sides. So we get 0 equals x squared because the x's cancels and the 1's also cancel. If you want to go ahead and, you know, like maybe you're in like autopilot and you go to square root both sides, there is no such thing as plus or minus 0. That would still just be 0 equals x. So there is only going to be one solution. It's going to be at 0, comma, and then we have to do the work to find what that's equal to. So if I plug the x back in, and it technically does not matter where, my y is going to be equal to x minus 1, so that will be 0 minus 1, which is a -1. So my final answer is at 0, -1. Okay, on to the back. The attendances y for 2 movies can be modeled by the following equations, where x is the number of days since the movie's opened. So we have the Top Gun and Top Gun Maverick and Guardians of the Galaxy Volume 3. When is the attendance for each movie the same? So to find this, I'm going to set my two equations equal to each other. So we're going to have a -x squared plus 35x plus 100 equals a -5x plus 275. I want to keep my x squared positive just because it makes my factoring easier. So I'm going to add x squared, subtract 35x, and subtract 100 from both sides. That cancels, cancels, cancels. We're left with 0 equals a positive x squared. -5x minus 35x is a -40x. 275 minus 100 would be 175. So I'm looking for two numbers that add to equal to a negative 40 and multiply to equal 175. So I'm going to guess and check, try to find some values. So let's see. 175 is not divisible by 2, not divisible by 3, not divisible by 4, but is divisible by 5. Specifically, it would be 5 and 35. Now, in order to make this work, I need them both to be negative. So a negative 5 and a negative 35. So this factors into 0 equals x minus 5 times x minus 35. So we set each of these equal to 0 to solve. We get our first solution of 5. Set x minus 35 equal to 0, get our second solution of 35. So it doesn't actually specifically say like what is the attendance on those days, but those are the 2 days where the attendance is the exact same. So at day 5 and day 35, the attendance is the same. So you can maybe argue like, oh, they're equally as popular. However, that kind of gets into how these, the attendance was modeled with a quadratic function versus a linear function, but we're not going to get into that. Okay, number 8, you and a friend are driving boats on Lake Talquin. Your path can be modeled by the equation y equals a negative x squared minus 4x minus 1, and your friend's path can be modeled by the equation y equals 2x plus 8. Do your paths cross each other? If so, what are the coordinates of the points where the paths meet? So we're going to set each of our equations equal to each other. Okay, equals 2x plus 8. Okay, when solving for this, I've said it again or multiple times, I like to keep my x squared positive. So I'm going to add x squared to both sides. I'll add 4x to both sides. And I'll add 1 to both sides to keep my x squared positive. So on the right side, combine like terms, we just have the x squared. 2x plus 4x is 6x, and 8 plus 1 is 9. So now I'm trying to think of two numbers that add to equal 6 and that multiply to equal 9. We'll think about it for a second, realize that the only two numbers that would work would be a positive 3 and a positive 3. So our perfect square trinomial. So our factored form would be 0 equals x plus 3. And you can either write it as x plus 3 times x plus 3. Maybe I can't even write that. There we go. Or you could write it as 0 equals x plus 3 squared. You'll get the same answer either way. So we're going to set our factor equal to 0. And we get the value of x equals negative 3. Now, a little awkward because I understand we're talking about driving boats, but maybe we're talking about it like it's on a grid. I know I immediately went to like battleship and thinking about that, which I understand there's none with that, but like if it's gridded out, like maybe on a coordinate plane. So the point of intersection would be at negative 3. And then to find the y value of the point of intersection, we just need to plug that back in. To me, I would rather plug it back into my linear function, which was that 2x plus 8. So we'll have y equals 2 times negative 3 plus 8. So that would be a negative 6 plus 8, which is equal to a positive 2. And that makes this my final answer. Okay, number 9. Solve the system by graphing. Okay, so for this problem, You can kind of either work around like I can't really force you into using graphing when I give you the algebraic functions. So I'm going to solve it both ways just so you're familiar with both. And then you can kind of decide from there what you prefer. So graphically, I'm going to do my first function in, what was that, navy blue, purple. So to find the vertex of my first function, I'm going to do my formula negative b over 2a. So that would be a negative 9 over 2 times a, so that'd be 2 over negative 2. So a negative 9 over negative 4 is going to be equal to 2.25. So I know at the x values, it'll be somewhere around here. To find the y coordinate of that, I'm going to plug in my 2.25. So this would be a negative 2 times 2.25 squared plus 9 times 2.25 minus 7. And after plugging that in, let's see, grab my calculator. Let's see, first we do our exponents. So 2.25 squared is equal to 5.0625 times a negative 2 would be a negative 10 times 0.125. I'm going to add that to my 9 times the other 2.25 minus 7. So we get 3.125. That's not a fun number. Okay, so at 2.25 and then a little bit above 3. Okay, for this function, right, I'm kind of feeling right now because we're getting a lot of decimals, my graph is not going to be super accurate. So I'm kind of hesitating on pursuing this graphing idea, but I'm just going to still go for it. Next thing that makes this easy, the y-intercept is over here at -7. So we're definitely going to have that. Your axis of symmetry is always going through your vertex. So from here, I know it's going to look something like this. Just to get it, let's see. So this is, so it's 9 little grid marks on the left. So it'll be 9 little grid marks on the right. Cool. So it'll look something like this. Okay, I'm just going to go ahead and get that second function on the graph just so we can verify like what it's looking like. So again, we're going to go through the same process of finding our vertex using the negative b over 2a. So that's going to be a negative b would be a negative 6, which will eventually be a positive 6 over 2 times a. So 2 times 1. So I'm looking a little bit nicer. A positive 6 over 2, which is 3. So my second axis of symmetry will be going through positive 3. Okay, and then to find the y coordinate of the vertex, I'm going to plug that 3 back in. So we'll have 3 squared minus 6 times 3 plus 5. So I plug this in. 3 squared is 9. 6 times 3 is 18. So I have 9 minus 18 plus 5. That is equal to a negative 4. So the vertex is going to be at 3, 4. So on this axis of symmetry, I go down 4, and that's my vertex. Then I see my I see my y-intercept is at positive 5. So I'm going to put it up here at positive 5. And I find the symmetrical point on the other side. See over here. 1, 2, 3. Cool. You could also do this finding the x-intercepts, which looking at this, it's looking like it actually could be at the x-intercepts, which would be kind of cool. Actually, it's maybe just at that 1. but we're not certain. So this is where solving algebraically is kind of the better choice. But I can see that my two parabolas are going to intersect. It's just a matter of precisely where are they going to connect. So again, this is kind of a fault of solving by graphing, but I still wanted to go over how to graph parabolas because we have discussed it this week with systems. Okay. So from here, I'm going to, sorry, some kids just walked in. Graphically is not the strongest because there's some human error. So I need to solve algebraically. So I'm going to set my two equations equal to each other. So I'll have a negative 2x squared plus 9x minus 7 equals x squared minus 6x plus 5. So to keep x squared positive, I'm going to add 2x squared to both sides. I'm going to subtract 9x from both sides, and then I'll add 7 to both sides. So 0 equals 3x squared. Oh, I didn't actually add 7 to the side, did I? Minus 15x plus 12. Thankfully, this factoring is not going to be terrible because it has a GCF of 3. So I take that out. Let's see, so x squared minus 5x plus 4. So my two factors that add to equal a negative 5 and multiply to be 4 are going to be a negative 4 and a negative 1. Okay. So we'll have, let's go up here, you got space. So we'll have x minus 4 times x minus 1 equals 0. My GCF of 3 is technically still out there, but it doesn't provide me a solution. So it was actually the end of the world if I forgot it. So the two x value solutions we got are a positive 4 and a positive 1. Let's think about if that currently matches my graph, which it does right here. So I see that this first value, it's looking like it's happening right at 1. And then the second point matches up that it is happening at positive 4. So surprisingly, my graph is not that inaccurate. And I'm seeing these solutions on our graph. To verify that my y values are correct, just because there's some potential with this decimals, let's just finish and plugging in. Now, to me, this bottom equation looks easier. So I'm going to choose the plug in there. So we'll have y equals plugging in positive 4. Okay, then I grab my calculator. So 4 squared is 16. Negative 6 times 4 is a negative 24. Plus 5 would give me a negative 3. So actually, this verifies actually that my graph is not perfectly accurate because that should have hit at negative 3, which not great, not the worst thing, but definitely would have been off by about 1. Plugging in my second value of positive 1. We have 1 minus 6 plus 5 would be 0, and that is accurate on the graph for my second point of intersection, so my second solution. Okay, 10, 11, and 12, we're actually going to solve these all the same way with my substitution. So we're going to substitute in, this is y equals, so I'm going to plug this function in for y. So we're going to have x squared plus, and instead of y, I'm going to have 2x squared plus 6x plus 7 equals 4. combine like terms, x squared plus 2x squared is 3x squared. Oh, and I have to set this equal to 0, sorry. So let's subtract 4. Get that over with, so plus 3. Okay, then to factor this, I'm going to take out the GCF of 3. Okay, then I'm trying to find two numbers that add to equal 2 and multiply to equal 1. And that would be x plus 1 times x plus 1. So those add to equal 2 and multiply to be 1. So my two x value solutions are going to be at -1. You don't need to write that out twice. It would just be, I don't know what's passing. There we go. So just the one ordered pair at -1. To then find the y coordinate of this value, we're going to plug back in. Does not matter where. To me, this bottom equation looks easier, less values. So we have x squared, so that'll be a -1 squared plus y, we don't know that, equals 4. That's 1 plus y equals 4. So subtract 1 from both sides, y equals 3. And that concludes that point of intersection. Okay, our next problem, starting off the same way, I'm going to set, or the substitution is setting it equal to each other works because they're both y equals. I just substitute in technically like this one in for that y value, which makes it look like I'm just setting it equal to each other. You don't want to use elimination on these because you could eliminate a potential solution. So generally we stick to substitution and graphing. So I want to keep my x squared positive, so I'm going to add x squared to both sides. I'm going to subtract 2x from both sides, and I'm going to subtract 5 from both sides, so that my equation is now equal to 0. So we'll have 2x squared plus 16x plus 30 equals 0. Then we're going to take our GCF of 2 out. So we have 2 times x squared plus 8x plus 15. I'm looking for two numbers that add to equal 8 and multiply to be 15, and that would be 5 and 3. So we'll have x plus 5 and x plus 3. Okay, so our two x value solutions are going to be at -5 and -3. I am going to plug these back in. I don't think one equation looks significantly easier than the other. I'm going to go back into this bottom equation just because I like to keep things positive. So we'll have, let's see, so for a coordinate point at -5 and a coordinate point at -3. So plugging in a -5. This is going to be, I plug this into my calculator. So we have a -5 squared is 25 plus 18 times the -5 plus 35. That would be a -30. Okay, then we're going to plug in y equals our -3. And we're going to type that into our calculator. So we have x. Just double checking something real quick. So when I plug all of that in, I get the answer of -10. So those are our two solutions. Really testing your algebra and factoring skills on this paper. Okay, last question on this paper. We have two quadratics. I'm going to set them equal to each other. So we'll have 2x squared plus 6x plus 5 equals a -x squared plus 6x minus 10. I like to keep my x squareds positive, so I'm going to add x squared to both sides, subtract 6x from both sides, so that's looking a good sign, and then add 10 to both sides. So we have 3x squared, those actually cancel, 5 plus 10 would be 15 equals 0. Okay, so I was happy to see that those x terms canceled out because it meant that I wouldn't have to factor or use the quadratic formula. We can just solve by square rooting. So to do that, we're going to subtract 15 from both sides. So I have 3x squared equals a -15. Then we're going to divide both sides by 3. Then we get x squared equals a -5. My next step would be to square root both sides. But once again, we have a negative under the radical. So that would be imaginary. So this is a no real solution, because they would be imaginary and we're not looking for imaginary solutions here.